Okay, so I think we should start because the flow is still coming, but I mean, probably will be continuous for a few minutes more. So good morning, everybody. My name is Elena Valker, and I'm the Junior Past President of the Control System Society, which is an elegant way to say that I'm the past president, but the youngest of the past presidents, since I served in 2015, last year. As you may know, the Bode Lecture Prize of a certain year is chosen by the president of the Control System Society of the previous year, which is exactly the reason why I'm here on this podium. So the Bode Lecture Prize aims at recognizing distinguished contributions to control system science and engineering. And part of the award is a plenary lecture that the awardee delivers at the CDC. I would like to say that choosing the 2016 Bode Lecturer is what I regard as one of the privileges that I had during my term as president. Richard Murray was my first choice, and I had no hesitations about it. Even if I have to tell you that he tried to convince me there were more deserving candidates, but the fact that he was so humble just to try to convince me of something like this just convinced me even more that my choice was the right one. Indeed, I've always been aware of the quality and the impact of Richard's research since a long time. And a couple of years ago, I had the pleasure of listening to one of his talks that I found so amazingly inspiring, and that, I mean, absolutely convinced me that he was my best possible choice for the Bode Lecturer. Richard Murray received a master's degree and a PhD from the University of California at Berkeley in 1988 and 1999, respectively, and is currently Thomas and Doris Everard Professor of Control and Dynamical Systems and Bioengineering at Caltech. Reading this title, I wonder how long is the office tag on your door, because just to contain all this information. His most recent research interests include novel control system architecture, biomolecular feedback systems, and network control systems. As you may have discovered yesterday during the award ceremony, he will also be the recipient of the 2017 IEEE Control Systems Award. Please join me in welcoming Richard on the podium.
Well, thank you, Elena, for that very kind introduction, and it's my pleasure and honor to be here and be able to give this lecture this morning. I want to say a little bit about the picture that's up here. I was wandering around San Francisco a couple of years ago, and I saw this truck. This is actually a cement truck, and this is really what was on the front of it, right? It says, "Here comes Bode," right? I said, oh my God, I have to take a picture of this. I'll get to use it in some class or something like that. Little did I know that the first opportunity that I would get to use it was, in fact, to give the Bode Lecture. And so it was a particularly pleasant surprise. The other thing that I learned just this morning was that the name Bode, it's a family name, but it came originally in the Netherlands from the person whose responsibility it was to take the information from the city council and deliver it to the city population. And so I think that's a very fitting name for this particular prize. And so I've learned many things about this. The other thing I want to say about this lecture is you get a year to think about this. So Elena contacted me over a year ago. And so you know, what do I want to talk about, et cetera. And so I had to decide, what should I give a talk about? And so I sent an email to a couple of people, and one of them was Siva Banda. And Siva wrote back and said, well, Richard, you should talk about this, that, the other, right? And so if you want to see what Siva told me to talk about, read the abstract, because that was his email back to me. And I decided that it was so good that I would just use it as the abstract and try and give a talk around that. So that's where this talk came from. Okay, so what do I want to talk about today? I have a couple of goals. So I'd like to talk a little bit about some of the history of predicting the future, because I've been involved in a couple of activities in looking at future directions and control, and I'd like to say a little bit about sort of how some of those activities went and where it went. I'll also describe a little bit about some of the things we missed in looking at the future in the past, and some of the things that we didn't kind of take into account, and that maybe we should have. And then I'll give a couple of ideas about sort of possible futures for control. And so I'll start by talking about what things looked like back in 1995 when I started my career in 2003. These were two particular times when I was involved in maybe making some predictions about the future. And then say a little bit about what I think decision and control systems look like today. And then talk about some of those possible futures, and obviously giving you my personal bias from that point of view. So I want to start by just saying a little bit about what is control? Right? We all have this problem, you go out, you're sitting next to someone on a plane, they say, what do you do, right? You have to decide, well, what do I really say I do, right? Do I say I do control theory, because then I've got to explain it, right? All of these things. But even within the field, I think we have to decide, what is control? And in all of these kind of future directions, we always have to say something about, well, what do we think control is? And of course, the traditional view is that, and this is the one I typically use in my class, right, is that control is the combination of sensing, actuation, and computation in a feedback loop to provide stability, performance, and robustness, right? So this is one view of what control is, and we think about cruise control and thermostats and aircraft and all of these things as examples of that. But I think that this is changing some, particularly in the last 15 years or so. And the emerging view that I would espouse is that really control is a collection of tools and techniques for analyzing, designing, and implementing complex systems in the presence of uncertainty. And in particular, it's this combination of dynamics, interconnection, communications, computing, and software that make controls work. And the types of applications that you see on the right are the sorts of things where control is having a big impact, whether that's self-driving cars, or synthetic biology, or large-scale network systems, battle space management systems, whatever those applications are, these are the types of things that we need to be dealing with. And I think my definition of control these days would be that control is the field that combines dynamics, uncertainty, feed forward, and feedback, and allows us to design these very complex systems. And so this notion of dynamics, uncertainty, feed forward, and feedback, just in case you forget, if you're a Simpsons fan, you can remember Duff beer. And so Duff is I think should be the official beer of the Control Systems Society. And we'll remember that it's dynamics, uncertainty, feed forward, and feedback. Now, there are a couple of principles, I think, that go along with that. And these are really unchanged over time. I think that one principle in control systems is that feedback provides us a tool for managing uncertainty, both uncertainty in the system and uncertainty environment. Feedback and feed forward also provide us tools for the design of the dynamics of a system by combining sensing, actuation, and computation into the physical, chemical, biological information systems that we build. And these two properties together give a very important corollary, which is that feedback enables subsystem modularity and interoperability, and that's what allows us to manage complexity at scale. And really, as we go forward, complexity at scale is the big challenge. And the control systems community is going to play a huge role in thinking about how do we design complexity at scale. Okay, so as I mentioned, I've been a couple of times involved in thinking about future directions in control. And the first of those was back in 1995. This is what 1995 looked like. This was my web page at the time. I was an assistant professor of mechanical engineering at Caltech. Just starting, getting going in the field and trying to think about, well, what is it that I want to do? What is the future? And so for some reason, right, blogs didn't exist, Twitter didn't exist, et cetera. And so, you posted stuff on the web. And so I created a web page that was the top 10 research problems in nonlinear control, right? Why I thought I was, sort of qualified in any sense to write these down, I have no idea, but I did. And this was the time of David Letterman. So those of you who are old enough remember they used to do these top 10 lists, right? You start at number 10 and, count down all the way to number 1. So I ordered it that way, and so I put these down. And so I won't go through all of these. You can sort of read them. But, a couple of them that were up there that turned out to be important in terms of what I actually did was this notion of using experiments to drive theory, thinking about writing good software for implementation of control, and transition to industry, right? How do we actually get these results to make a difference? And so I put these down in 95, and then sort of sat in my office and thought about these a little bit. And about 3 months later, I wrote down some new ones. And so I updated the page. And so then now there's a previous rank, and so you can sort of see where things were at. And if you go hunt around a little bit on the web, you can sort of find these and click on the links and see what they go to. And in August of 1995, sort of 3 months later, I decided that writing good software had gone from number 3 to number 8. Number 2 was a new one, magnitude and rate saturation. I must have been doing something where all of a sudden I'm going, oh man, this stuff's really getting in my way, right? And then the other one was convince industry to invest. So clearly I'd had a bunch of grants turned down, right? And I was needing money, right? And so the number one problem, right, in nonlinear control at the time was me getting money so that I could actually do the work in nonlinear control. So then about 5-6 months later, I updated it again. And so here's what it looked like at that point. You'll notice that Convince Industry Invest had dropped to number 9. Clearly my NSF grant got funded. This was no longer a priority. I didn't have to worry about this anymore. Writing good software suddenly popped back up to number 1, right? So you can see a huge amount of variability, right? Writing good software went from number 3 to number 8, back to number 1, right? So I had no clue what was going on. I think that's what you learned from all of this. Now, there was one fatal flaw, well, there are many fatal flaws, but one of the fatal flaws in all of this was that this was just really me sitting in isolation coming up with this stuff, right? I don't think anybody was reading it, I wasn't getting any feedback on it, right? And so it was an interesting exercise to write some of these things down. It taught me a lesson, which is never post up on the web, that you don't want to have come up later. So if you go look on the web archive, you can actually find all of these old pages, even if I've deleted them and tried to make them invisible, they still exist. So, I got the opportunity to kind of address this flaw in 2000 when Mark Jacobs contacted me and said, hey, I'm putting together a panel on future directions in control, and would you be willing to be a participant in this? And so from 2000 to 2003, I participated in another one of these activities. And I have to say this activity absolutely shaped my view and my interactions and other things, because it was a fantastic group of people. This was the panel. These were the people on the panel. You recognize many of the leaders in the field that are up here, and people from different areas and other things. And interacting with this group of people had a huge impact. So why did this panel get formed? Well, the motivation for forming the panel was multifold. So one was that we wanted to try and articulate the challenges and opportunity for the field of control. We wanted to provide a compelling view of the field that would attract some of the best people, some of the new students that are coming in, new young faculty, et cetera. It was obviously important and continues to be important that fantastically talented researchers get interested in control and help move the field forward. And of course, we wanted to articulate ideas for funding, right? So what is it that the US government, this was a United States activity primarily, what is it that the US government ought to be funding so we can go out and do all of these great things? And the reasons for doing the panel at that particular time were also multifold. One was it had been about 12 years since the last such report had come out. Wendell Fleming had led an activity that led to a SIAM report on future directions and control. And so I think that people felt it was time for an update of that activity. But the other thing was that the field was changing at the time. There were a lot of new applications that were coming out. UAVs were very hot, unmanned aerial vehicles. The internet was starting to have a big impact in terms of the way we design control systems. Robotics and RoboCup and all of these things were out there. Systems biology was blooming. And I think, importantly, this increased importance of complex systems and the difficulty in getting those to work was sort of sitting there. And people, what are we going to do about this? How is the controls community going to contribute to this? And so what we did was that we organized the activities of the panel. So there was a small organizing committee consisting of 6 of us, Stephen Boyd, Roger Brockett, John Burns, John Doyle, myself, and Gunther Stein, who took on the task of sort of organizing how all of this was going to go. And so we organized a workshop in June of 2000 that we held at the University of Maryland, and Krishna Prasad was kind enough to host us, and his students helped out with all of the arrangements. And we invited a wide variety of people. So you may or not be able to read all of these things, but this is the list of people who participated in that workshop. And again, we tried to get a broad spectrum of people from many different disciplines, from different parts of the control field, for different application areas and all those things. And we kind of organized this in some sense across the different categories, people from academia, people from industry, people from government, but also across different application areas that we thought were going to be important: biology and medicine, transportation and aerospace, information and networks, materials and processes, robotics and intelligence and machines. And this tells you some about, at that time, what we were thinking about. And then we recognized there were other areas as well, and so we put that as the category. And so we got together at this workshop and we tried to talk about what are all the big areas, and we took all of that information and started synthesizing that into a report. We did multiple rounds of this report, sending it out to people, getting feedback, coming back, right? Sort of using this idea that we could improve this through iteration. And in January of 2002, we came out with what was essentially the ultimate draft of that. And we released the report in April of 2003. And then we had to do some things to put it into an actual form in which we could get SIAM to publish it and other things. And so it was published about a year later. And so, now on order, 15 years ago, was when all of these ideas came up. And so it was a very interesting process. And of course, we sort of finished and said, fantastic, what next? And of course, what we hope happened next is that, profit, right? And so if you remember Star Trek and the Ferengis, right, that was always the final step, right? Profit comes out of the end of this. So we were hoping for that in this case as well. If you'd like to see what we were doing at that time, including all of the panels and the meetings and the PowerPoint slides, et cetera, it's actually still up on the web. And so you can go to this web page, and if you just Google future directions in control dynamics and systems, you'll get to this. And eventually we came out with a report, and this is what it looks like. It's available for free from that website. You can actually, I think, still order the physical copy from SIAM if you're interested, that tried to pull together all of these ideas. And what's in the report, we organized it into an executive summary that tried in a few pages to sort of describe why this was exciting. And then a next chapter that was a little bit longer that gave an overview of the field, what is control, along the lines of what I just talked about, the increasing importance of information-based systems, a summary of the opportunities and challenges. And then in each of these application areas, we went through and talked about, right, what is happening in this area, why is this important, talked a little bit about education and outreach, and then made some recommendations and tried to justify those recommendations. So that was what we put into the report. And there were 5 primary recommendations at a high level that came out of this. And those 5 were, first, to increase the integration of control, computer science, communications, and networking. Second, to increase the research at higher levels of decision-making, moving towards enterprise-level systems. Third, to explore high-risk, long-range applications of control, and we listed a bunch of areas that one might consider doing that in. Fourth, to maintain support for theory and interaction with mathematics, because we felt that that was something that had been very important for the field. And fifth, to invest in new approaches to education and outreach to non-traditional audiences, right? To really make control something that was used more broadly than just the controls community itself. And so those were the 5 recommendations. And if you sort of look back and say, how'd we do? I think we actually did okay on most of these. So certainly if you look in the first area, there are now things like the technical community and network systems within IFAC, the Cyberphysical Systems program at NSF, the transactions on nonlinear control, network control systems within the Control Systems Society, and many other things that line up, I think, with this first bullet, this first recommendation. In the areas of control at higher levels of abstraction, there's a lot of work in formal methods and other things that's now becoming more prevalent. Smart grid, smart transportation, smart infrastructure systems. And in fact, within the Control Systems Society, we now have technical committees, a couple of technical committees on smart stuff. And so, I think this is something that we've started to see happening. In terms of high-risk, long-range applications, we heard a plenary on Monday on quantum systems, so that's certainly something. My own work in synthetic biology is another example, and there are many people in the community that are doing that. Geoengineering is another area, not so much represented at this conference, but one where I think controls people are very much needed to think about, what should we do about engineering the climate if we need to do that, and we go that route. This fourth recommendation on maintaining support for theory and interaction with mathematics, I think, is one where we maybe haven't done as well as we should have. My own personal feeling is that especially the interaction with mathematics and the support for just basic theory with no application is slipping a little bit, at least in the United States. You really have to be able to articulate what the application is if you want to get support in the US, I feel. And so that's something I think that hopefully other countries are doing better than we are in the US, but I think it's an area where we haven't done as well, and maybe we didn't articulate it as well as we could have. And then this last area of really broadening beyond the traditional audiences, I think is also an interesting one. There are a number of new textbooks that have sort of pointed to this. One of my favorites is this one. This is Feedback Control for Computing Systems. This is written by a computer scientist talking about control and PID in computing systems, large-scale server farms, et cetera. It's a great read if you haven't seen it. In particular, there's an appendix that completely trashes all of the traditional controls textbooks, including the one that I wrote with Carl Ostrom. And so you can see why they think we're not going out and doing this and why they think they need to go do it themselves. And so the computer science community is going out and doing that. But I think it's great that, computer scientists are recognizing the importance of control in what they're doing. One written by people from our own community, Pedro Salvardos and Ema Mariels, is Feedback and Control for Everyone, quite a bold title, right? And so we're just going to go out and manage to teach this to everybody. And I think it's fantastic that people are starting to do this. And again, it lines up with this one. And even here at CDC, so right after this session, John Doyle is running a session on teaching control theory in high school. And if you went by the booth and tried to control the steering wheel and other things, you can go find out, how does all of that fit, and how do we teach control theory to people who in high school aren't going to know about eigenvectors, eigenvalues, certainly not Laplace transforms, right, and all of those things. But the basic principles of control are pervasive, and we need to think about how do we teach that at all levels. The other thing I think, this is a good point to say, is that it's been about 15 years since we did this report, and so I'm pleased to say that there's another report coming out, Systems of Control for the Future of Humanity, so we're up in the ante here a little bit. So this will come out hopefully by the IFAC World Congress in April, and so, or in July rather. And so there's another iteration coming that many people in the community have contributed to, and I had the honor to contribute to a little bit. Okay, so I think overall at that time we did a pretty good job of looking at what the future might be, but we did miss some things. And so what were the types of things that we now, looking backwards, right, we should have said, boy, how did we miss that? And this is my personal opinion. I'm sure all of us can write many things that we missed. One, I think, was cloud computing, big data, and machine learning, the impact of all of that. Right? I remember these pictures. I picked one of them here, where people were sort of saying, oh, it's all going to be up in the cloud, right? And I'm going, what the hell are you talking about? This makes no sense to me, right? I just didn't get it, right? Why is that going to matter? We have computers. Computers can compute stuff, right? They're in my lab. I don't understand why sort of putting the computers on the other side of a network far away is going to make a difference. It's made a huge difference, right? This completely changes the way we think about data, learning, algorithms, and other things, right? And as these systems get bigger and bigger, I think that we're going to see more and more impact of that, right? And if you look at things like 5G networks and other things that are coming, they're very much focused around how do we start doing control around these things at different time scales and different things, and really taking that account. So I think this is something that we kind of missed. And the notion that data was sort of a second-order thing. You took data and processed it in a model, and then you used the model. I think data as a first-order object. Data is my representation of what a behavior is going to be, and I operate on the data directly is something different that, looking back, we probably should have seen some of the initial signs of and maybe done something about. Another that kind of comes along with this a little bit is security and privacy. We really said very little about security and privacy in the report, and I think it's a huge deal. Stuxnet came around in 2010 and demonstrated to everything that the control networks that we're using around the world in SCADA systems and other things were not designed with security in mind. And so I think we're going to have to think about that a lot harder. Privacy is an area that even now we're just starting to think about. Not nearly enough, right, as we start sharing all of the information, but also all of the safety critical and other types of sensitive information that might be getting used in these systems as we start moving towards the Internet of Things. And so this is an area that we really didn't recognize at that time. If you go look in the report, you won't find, probably if you search for the word privacy, you may not find anything. So that was certainly something I think we missed. Another that I think we missed was the interaction with humans. And the robotics community has done a great job here. There are lots of different areas where this comes up. One is just self-driving cars. And I've put an autonomy car up here because there's people from the controls community that are very much involved in autonomy, as with many of the other autonomous car companies and self-driving car companies. But the notion of how do our autonomous systems interact with humans, both the human sitting there. We talked a little bit about aircraft and human in the loop and on the loop in the report, but we really didn't think about, I think as much as we could have, the role of humans in a society interacting with machines and what's going to happen when 10% of the cars, 20%, 50% of the cars on the road are self-driving, but not 100%, right? So now there's an interaction with humans in society that we have to think about. Another that I think we didn't necessarily spend quite enough time was the role of energy and sustainability and what control can do in that area. We had a little bit of that. We certainly had smart grid in the kind of control of networks section. We had some notions about geoengineering as one of those areas. But again, I think energy and sustainability going forward are huge areas, and we didn't quite highlight it in the way I think we might have. So there were things that we missed. I think we've caught most of these in the upcoming report. I hope so. And certainly people are working these areas. We missed it in the report. Doesn't mean we missed it as a field. But I think one thing this does say is that with all of the other things going on, right, there's still lots of work to be done. So the good news is it's a fantastically interesting period with many, many, many things to be done. Okay, so what has happened over the last decade or so? I think that we've made tremendous advances as a field. And so one is that optimization-based control is now something that just happens. So this is a video of the Caltech ducted fan. This was something that Mark Milam built. This was some experiments that Mark and Nicolas Petit were running. I think Nicolas is actually hiding behind the pole there. If you see there's a person, just in case the system doesn't quite do the right thing. And this is a system that was running receding horizon control, running at about a 10 hertz update loop, calculating out what to do for the next 10 seconds. At the time that we did it, we had to buy a $30,000 computer in order to sort of compute fast enough, right? Not anymore. Right? And so we all know, we've already seen it come up in probably almost every talk, right? The role of receding horizon model predictive control online optimization is huge. So that's certainly a huge advance that I think we've done. Another is thinking a little bit more deeply about the role of layering architectures and network control systems. This is a video from the DARPA Grand Challenge showing one way in which we can think about this layering. So the decision making that's happening as we're driving and we're having to think about low-level things. How do we stay centered on the road? How do we drive at the right speed? Higher level things, what road should I go on? Should I turn left or right? Higher level things, when I come up to an intersection, what is the interaction with the vehicles at that intersection? So as I come up to an intersection and I see a car stopped, I need to know that that car is stopped. I need to stop behind it. I need to wait until it goes. Once it goes, I need to drive up to the intersection, right? And of course, this is the precursor for many of the things that we see in self-driving cars. This was a project that was done by a bunch of Caltech undergraduates, right, using some of the advances from our field. So I think that this is an important area as well that we've made great strides in. As I've already mentioned, I think one of the properties of control is that it allows this modularity that allows us to connect stuff up together very quickly and get very complex systems working together. Another area where we've seen a lot, and I'll say a little bit more about it in a minute, is in the use of formal methods and combining ideas from computer science. This is a graphic of something we call the RoboFlag drill. It came from discussions with Raf D'Andrea, who was at Cornell at the time. And this was a distributed protocol for trying to block a bunch of incoming attackers. So we were thinking about this as you're playing soccer and you've got a bunch of people coming across the field and you want to sort of guard each one of them. How do you do that in a distributed way? What information do you have to share? And it was a nice example of something where we wanted to prove that we could actually satisfy some property. So it was an example of applying these formal methods and thinking about hybrid and discrete systems and kind of the things that we're doing now in cyberphysical systems as a community. And then the last area, I think, in which we started to make a lot of progress, this one's still a little bit more in its infancy, is thinking about moving to these enterprise scale systems. And in particular, as we look at things like the Internet of Things and other things, the industrial internet, this is a GE term, I think that this is an area that we see happening in the world around us, and many of us are participating in. The 5G communication network standards that people are talking about, they're talking about 50 billion devices, right? So how do we do things at the scale of some fraction of 50 billion devices, right, all managing our infrastructure systems and other things? So I think that that's something we're starting to see happening technologically, lots of future things we can do. Okay, so as we look back, I think that we sort of see what we were looking at, some of the things we missed, but a lot's happened, and I think it's a sort of fantastic area. I want to talk a little bit about a couple of areas, and one of them is to sort of, what do things look like today in the area of network control systems? And so, I think as we think about what does the design process look like today as we design these complex systems, it's coming together quite nicely. There's still lots of work to be done, but it's coming together quite nicely. We start with some physical system that we want to control. And of course, as control engineers, and I think increasingly we're getting involved in this very early in the system design, the first thing we do is we put together a model of the system, a model of what the environment that the system is going to see. And we use that model to sort of say, will this physical system satisfy it? Have I sized the actuators right? Can I turn the steering wheel fast? All of those sorts of things, depending on what the system is. And if it's not quite right, we use that model to do design iterations, right? So we'll iterate on this design, and then get it to where at least we have a nominal system that can satisfy the specifications. And then we'll start to design the feedback loops that go around that, perhaps starting with the inner loops and the lower level things where we're using sensors and simple Kalman filter processing and other things, and PID loops and their ilk. To do things. And again, at this stage, we may find out that, the Bode integral formula tells us that, you can't actually get all that you want out of this now that we start looking at the feedback properties and the noise rejection and other things. And so we may do new design iterations. So those design iterations may change sensing and actuation, may change the computational framework, the architecture, and other things. And then we move progressively to higher levels of abstraction. So we move to an optimization-based layer where we'll start to do more complicated types of state estimation, maybe moving horizon estimation, particle filters, Bayesian inference types of things. On the control side, if you want, we'll do things that look more optimization based in terms of model predictive control, receding horizon control, and those sorts of online optimizations. And again, we may do design iterations here as we do this. And finally, we'll put on what's essentially the decision-making layer. And of course, this layer itself may have many layers above it. But thinking about modes, contingencies, the supervisory control types of things, managing constraints, and the other things that go there. And so I think as we design these systems, we've gotten used to thinking about these at multiple layers of abstraction and thinking about what happens at each layer of abstraction. One important thing about this is, again, one of the key things is we've got dynamics, uncertainty, feed forward, feedback. You see all of those here. The uncertainty coming from the environment, we have to remember it's not just interacting with the physical system, right? It's really interacting with the entire stack. Right? And so it really pervades across all these levels. At the decision-making layer, we have to think about, what if I'm self-driving car, I have to think about what's the environment doing, right? And how do I treat that information? Another thing, of course, that's happened and that we now use is that these are typically going to be network control systems, and so we have some sort of networking communication infrastructure that all of this interacts with. And again, this pervades the entire stack, right? So we can use that to interconnect these pieces in interesting ways. And those interconnections enable new things. Now, one of the things that I think that those new interconnections enable, and indeed the increase in computation and cloud resources and other things, is a shift from use the model at the design stage to actually using the model online. Right? That is that we may have an online system model that we update online, right? And we redesign the controller essentially using our current model. Right? And so the notion that, as our system changes, our model changes, and by the way, I've taken the design protocol and put that into the system via some online optimization or receding horizon control, for example, right? Or a Kalman filter that's using the current model. And so this has been enabled by really all of the kind of computing and communications infrastructure that's happened over the last decade or so and that we're now starting to take advantage of. Now, one of the other things that networking infrastructure allows is it allows us to throw much more computation at the job. And so now we don't think about just having a single state estimator, a single online optimizer, a single decision-making protocol, a single feedback controller. We may have multiple ones of these all running simultaneously. They may be running across different agents that are connected together and doing things. They may be running at different layers of abstraction within one of these kind of high-level layers. And so that really makes a difference. But when we do all of that, of course, then we have to start worrying about the relative timing of all of these things, right? So even in our DARPA Grand Challenge vehicle, we had hundreds of threads of execution that are all running somewhat independently from one another. So how do we manage all of these things? And finally, The other thing that the networking does, of course, is allow us to connect to other subsystems, the cloud, users, and all of these things. And so this is what, when we design modern control systems, we're currently designing. And this is what we need to be developing the technology around and teaching our students how to do in different ways. So, of course, this is still control in the traditional sense of combining sensing, actuation, and computation. But it's also very much control in the sense that I would describe of using dynamics, uncertainty, feed forward, and feedback, Duff beer. And so I think that it's something that we can look for how to do all of that. And this is a problem that's not just, if a computer scientist looks at that, they go, yeah, this is what we do too, right? They might look more at the higher levels than the lower levels, right? But we really have to look all across these. So there are examples of this all over the place. Aerospace systems, self-driving cars, factory automation, process control, smart, everything. And so there's certainly lots of places that we see this. And this is the type of architecture, I think, that we see, right, certainly in the industries that I interact with. Now, there are a lot of challenges, and these are ones, of course, that people are looking at. One I think that's an interesting one is to think about these layers of abstraction and how do we connect the layers of abstraction. How do we define what those layers of abstraction are and what the interfaces are between them? And how do we define what the contracts are? That is, what do I assume about the lower layer at the higher level, and what do I assume about the higher level at the lower level, so that when I interconnect these two things together, right, across these layers of abstraction, it works. And we know from the internet and other things, right, that those layers of abstraction and the modularity within those layers, the ability to change the underlying technology, is a huge enabler for moving forward quickly. I think we also have to think about how we scale these to 50 billion devices or some fraction of that. And so you can think about that as how do we scale in the horizontal direction. And so think about those as horizontal contracts. So as we look at swarms and smart grid and other things where you have a bunch of systems that are at the same layer of abstraction trying to do the same thing but are interconnected, how do we think about, again, the contracts, the horizontal contracts now that might connect that together? And of course, all of this needs to be done thinking about stability, robustness, and importantly, security and privacy as we go through. So this is, I think, what we need to think about and what we're currently doing in terms of control systems. And so I want to talk about a couple of the pieces of this just a little bit to give more insight and say a little about where I think there's some opportunities to do even more. So one is in the area of formal methods and control. And so Claire Tomlin asked me to give a talk at Berkeley, and she gave me the title of the talk. And so it was rapprochement between formal methods and control. I had to look up what rapprochement meant. But it was quite nice, right? Sort of the bringing back together, right? So reapproach of these two areas. And I think that's a very accurate thing. So the discrete event systems community has been thinking about this for a long time, but really there'd been kind of computer science going off and controls going off, right? And now I think the two are starting to come back together, somewhat enabled by the history of the discrete event community in terms of doing that, but I think building more. On the controls community, we'll think about a block diagram that looks like this, with apologies to John Doyle for drawing the arrows backwards. And the type of specification that we might do here at a high level might be some sort of an H-infinity style specification, right, where we say that we want some output measures that we're doing, errors or whatever they are, to be bounded based on the disturbances, and also allow for system uncertainty, right? So we're going to capture that uncertainty. And so certainly here we see dynamics and interconnection and feedback, if not feed forward explicitly, although as we know in many of these systems there'll also be a feed forward component. Now, we can redraw that diagram just a little bit as something that might look like this. So now we've got a plant, a controller, some sort of environment, unknown environment maybe, or the delta block up there could represent system dynamics or environmental dynamics and disturbances. But I think an interesting question is to say, well, what happens when our description of all of those is in fact a discrete transition system, not differential equations or transfer functions? So now it's the same problem, right? This is the problem of how do I make decisions, right, at a decision-making layer of abstraction in presence of uncertainty with dynamics, right, for my system. I can't just make decisions arbitrarily for, say, self-driving and other things. I have to do so in a way that respects whatever the maybe rules are, specifications are, other things. And here there's also a natural specification language, and the one that I like to use comes out of formal methods. And this is a formula that well, probably 8 years ago I couldn't read, and so now I know how to read this type of mathematics. But it's a formula that essentially says, under the assumption that the environment satisfies some properties, safety and liveness properties, I want my system to satisfy some properties, safety and liveness properties. And something that happened now about a decade ago is that just like the H-infinity synthesis problem got solved in the sense that we now have good computable ways of solving this, this class of problems also got solved. And so this is a problem called GR1 synthesis. I learned about this from a student of George Papas, Hadas Kreskazit, and said, oh my God, this is huge, right? Because this is something that was new, right? And coming out of the computer science community. And what I like about these two problems, the H-infinity synthesis problem and the GR1 synthesis problem, is they're basically both of the same form. There's an environmental spec, right, that tells us something about both the disturbances and the unmodeled dynamics of the system or the environment. There's a system spec, what do we want it to do? And similarly, in GR1 synthesis, or in this class of formal methods problems, there's an environmental spec, as well as a system-level spec. And the synthesis problem is, given a model of the system and that specification, synthesize the decision-making logic that automatically makes that controller work. And we do this in controls all the time. An LQR controller, I give you x dot equals ax plus bu. I give you a cost function that I want you to minimize, and I call the LQR command, right? And so we want to do the same thing now on this other side. And so this is, I think, an exciting area. It is very much, in some sense, at the heart of things like cyberphysical systems. And of course, you can't just solve one or the other. Well, you can, but then you will be relegated, right, to your layer and not the layers in between. And so I think we have to figure out how to pull these things together and do this. And there are many examples, from aircraft to self-driving cars to the industrial internet, to do that. And broadly speaking, I think that we really are starting to get more serious and more rigorous about the control of these sorts of reactive systems. The systems are clearly too complex to be tested by trial and error. We must use more formal methods. The controls community is fantastic at using theory to help solve problems. The systems are much too safety critical to do this, so people probably know that for software, which is what control systems are these days, running in aircraft, you have to certify that your software, safety critical software, so things that might lead to loss of human life, have to be shown to be reliable, to have no more than one failure in every 10 to the 9th flight hours. 10 to the 9th flight hours is 100,000 years. How do you show that, right? You don't do it by testing, right? You have to do it by rigorous analysis combined with testing, right? And sort of think about that. The other thing I think that we're starting to see a little bit of is moving from this design then verify, here's the logic, go tell me that it does the right thing, to more of a specify then synthesize. Tell me what you want the system to do, and then I will automatically synthesize the logic. And again, the controls community has been doing this for a long time, right? We're starting to see this come up a little bit more in the hybrid systems and computer science communities. I think a next step of that is to think about what are the contracts that we need to use at the different layers of abstraction. Right? So that we can now synthesize the contracts. Here's what that optimization-based controller should do in terms of its specifications, so that when I connect it with a decision-making level and I connect it with a feedback controller, the overall system will behave in the right way. And so I think we need to think about how to do that, and some work is starting to happen there. Another thing that we're starting to see a little bit more is combinations or combining both data-driven and formal methods types of systems together with controls and thinking about human-like interactions. And again, self-driving cars is really pushing this forward as we have to think about, right, how do we make sure that humans can operate in environments that machines are operating. And finally, I'll just point out again, for about the 5th time, that we need to be incorporating security and privacy guarantees as we do this. We don't want to redo what we've done right before in SCADA systems and other things. It's not think about that, it'll get handled later. No, it won't. We got to think about it now. And again, these ideas of formal methods and control and other things, there's great connections between observability and reachability and things like privacy and security. And so I think that the tools can come together there. Okay, so this is, I think, an area that when I look out now, I sort of see lots of promise and lots of people working on it across the community. We see many things here at CDC about this. So where do we go from here, right? This is sort of what's happening and what's currently here. So I think there are some opportunities for the future, and I've sort of divided them into 2 pieces. One that I'll call traditional, and I don't mean it in a derogatory sense, but thinking about the things that we know that we do well. And so certainly one is what I've just been talking about. I think we need to continue our focus on rigorous design of complex systems. One of the things that in the last couple of years I sort of finally understood, people have been trying to tell me for a long time, I used to say, oh, Cyberphysical, how clever, they renamed hybrid systems, right, and they got more money for it, right? That's pretty cool, that's a good idea, right? Because you can't fund hybrid forever, right? So let's just call it Cyberphysical. But in fact, that's not right. Cyberphysical systems are different, right? Because they're really bringing a computer science perspective to the control of physical systems. So the cyber there matters. It's not just continuous and discrete. It's thinking about the things that computer scientists think about, right? And thinking about verification and model checking and scale and all of the other things that computer science has done so well. And really, that to me was like, oh man, I mean, I finally get it. I'm sort of working in this area, and it finally occurs to me why cyberphysical really is something that's kind of new and different. I think the other thing that we have to think about is large-scale systems. The Internet of Things is coming. It's an opportunity. It's going to have huge numbers of devices on it, and we're going to start connecting those together. The 5G networks, right? People should remember the fifth G stands for control, right? Because really it's putting in the time criticality and other things, right? That's one of the goals of the 5G networks, right? Is to get the time criticality down to where you can use it for feedback control systems. So guess what? We're going to get to use it for feedback control systems, but we're going to have subsystems that consist of thousands and millions of devices, right, that are being connected together. And so how do we think about that, I think, is a good one. And again, data, security, privacy, humans, the things we missed the first time around, let's not miss them this time as we go through. Now, the other thing is that I think in controls, we do need to think a little bit about how we communicate. How do we talk to non-traditional audiences? How do we communicate what we do? I remember John Doyle saying when we were back 15 years ago doing this panel, he says, the control theory community has done a fantastic job of making its field impenetrable to the outside, right? We've created a fortress, right? You cannot understand what we're talking about, right, unless you get a PhD in control, right? Good for us. Bad for us, right? I mean, not a good idea, right? So I think we have to think about how do we do this differently. And so I think we have to change, for example, how we teach. So I think we need to think about going from teaching people in aeronautics and chemical engineering, electrical engineering, mechanical engineering, civil engineering, to how do we teach controls to people in computer science or bioengineering or economics or physics. And they all have very different backgrounds. And so I think we've got to think about what does our course structure look like. So for example, I think that we should have a required course for all majors, not just controls, in feedback systems. We should talk about what are these key principles, right? The role that feedback can play in managing uncertainty, the role that feedback and feed-forward can play in design of dynamics. We need to do this in state space and frequency domain. Both of those are important. In many places, state space is the natural place to start. Probably mainly single input, single output at this kind of required class, and thinking about both analysis and design. Now, all of us have courses in control that cover these topics, right, at our universities. And my question to you who are educators is, can a sophomore or junior in computer science take that course? And if the answer is no, then we either need to change the course or offer a new one, right? But I think that every computer scientist, so every well-trained engineer should probably have a class in machine learning. Every well-trained engineer should probably have a class in feedback systems. We have to make that change, right, in order to make that class be accessible. So feedback and control for everyone is a start, right? So feedback control for computer systems is a start. But I think that the people in this room have to make that change in the way that we teach our classes and the way that we interact. Now, this is for everybody. I think also if you ask me, what's somebody who's well-trained in control and dynamical systems, for example, have? I think there are a couple of other courses. I would require that everybody in control and dynamical systems take some sort of an optimization-based control course, right? Really the feed-forward part, right? And especially with these online systems that we can now do. So real-time trajectory generation, optimal control, model predictive control, Kalman filtering, and what extends from it, particle filtering and other things. So I think that should be a required class for everybody, and maybe it already is at all the places. It certainly is at Caltech. I think we should also require automata theory and verification. Right? That is that if you're a control systems engineer, guess what? You're going to interact with a computing system, and it's going to have higher levels of decision making, and you better know what types of tools are there, right, to both understand and model that system, automata theory, and verify that. And of course, there's great research opportunities in connecting those two things together, but just understanding what modern model checking can do is, again, something I think every well-trained controls engineer, increasingly systems and controls engineer, should know something about. So I would require a course in that area. And finally, I think I would require additional courses in things like probabilistic systems, stochastic systems, or hybrid systems, other courses to take. And of course, additional advanced courses beyond that, right? But if you said, what do I want every single controls engineer to know about? These are probably the 4 course areas. I would say certainly the basics, something in optimization-based control, something in kind of computer science and modern computer science methods, and then some additional things for a little bit of breadth. And the 2 I picked out here were hybrid systems and probabilistic systems. So that's one. Another thing I think we ought to do going forward is to continue to get out of the box. And I use this because Roger Brockett was visiting Caltech, and I was sitting with him. He's probably back when that picture was taken. And I went and visited him in the office that he had at Caltech. And he said, Richard, I described to him what I was doing. He says, look, Richard, here's the thing. Here's the sort of space of all control systems. And you draw, you always drew on a piece of paper. Drew a piece of a box on a piece of paper. And then here's the space of nonlinear systems. And down in the right-hand corner, right, he sort of drew this box. And here's the space of linear systems. He drew a tiny little box. He says, now look at where the control community is. They're all crammed in this tiny little box, right? Good for you. You're in the next little box, right? Because I was doing nonlinear control, right? Get out of the box, right? And start thinking about what's going on in a bigger sense. And so I think that that's important. So again, I would say we should think about control as the field that combines dynamics, uncertainty, feed forward, and feedback, right? Have a couple of beers, think about what that means. I think we need to go from just thinking about things like ODEs, PAE, LQG, and MPC to thinking about computer science, machine learning, artificial intelligence, synthetic biology, economics, physics, right, as what we think about as a field. And I think in addition to coming to conferences like CDC and HSCC, we should go to things like NIPS and POPL and ICML. And if you don't know what those are, go look them up, right, because they're important conferences for us to be represented in, right, and for those people to be represented here. All right, so in the kind of mainstream areas, I think this is one. I want to also talk a little bit about what I'll call non-traditional. And here I want to build on this recommendation from the panel report back in 2003 about exploring high-risk, long-range applications of control. And I think in this area we have to recognize that this may be different than the more traditional ones. And in particular, we may actually require new types of sensing, actuation, and computation, plus new architectures that are tuned to that. And it may not be the same as what we do in other areas. And I'll use as my example here an area that many of you know I've been interested in for a while, of synthetic biology. And so here's what I'd like to do before I retire. I'd like to build the system you see on the right. This is a nanoscale machine. It has a bunch of subsystems in it. Right? It has a power subsystem called metabolism. It has a sensing subsystem, an actuation subsystem, a communication subsystem, a computation subsystem, right? All of these subsystems. And all of these subsystems are regulated and co-regulated, right? This is, for me, right, an autonomous vehicle. But this autonomous vehicle is a couple of microns long. And I don't know how to build that out of metal or other materials, silicon, et cetera. But biology knows how to build that out of molecules. And so if we think about that as a design problem, right, can we design a 1 to 2 micron long robot that can find a toxin and neutralize it? Or assemble a bunch of chemicals into food, right? We know this is possible, right? No question. Can we as engineers design such systems? And I don't care about the systems being living. In fact, I don't want them to be living. I want to design, I want to put it together. If I turn the power off, I want it to stop working, right? But I want to do it at that scale. And so I think if we think about that problem, that one may require us thinking about, okay, fine. What's the sensing system actually look like? What's the actuation system? How are you going to do computation? So, for example, this is some of the work that we've done in this area. This is a proportional control law. All right? So this is describing a genetic network that implements a proportional control law. Don't worry if you can't read it, right? But it uses sequestration as its mechanism for sensing. It uses transcriptional activation and phosphorylation as its method of actuation. And what it's designed to do is to keep two proteins in the same ratio to one another. It's an important metabolic function, right, is to keep these two proteins, say, in a 4-to-1 ratio, one to the other. And so RFP is one of the proteins. It's a fluorescent protein that we can see. GFP is the other, just for kind of testing purposes. In fact, we've implemented this and put it into cells. And this is what the response looks like. So the curve on the bottom is the input, and we're trying to maintain the curve at the top at a 4-to-1 ratio of that. And you can see, indeed, we're getting a good tracking controller at about a 4-to-1 ratio. So this is a molecular implementation of a proportional feedback controller from about 2 years ago. So you can see we got a long way to go to get to that top upper right diagram. Right? So there's a lot to do, and a lot of it is, what the heck's the sensor? What the heck's the actuator? How are we going to implement the computation? So I think in these long-range areas, don't talk to me about abstraction hierarchies and how to use linear temporal logic. Not there yet, right? Just figured out how to get proportional control work, right? Working on PI, all right? That's kind of the state. Okay, so I think advances are going to be required, though. These are very stochastic systems. They have huge amounts of uncertainty. The traditional models that we use are probably not the right ones. And I think that the control architectures are likely to be different here, right? Again, we're going to have to continue to focus on dynamics, uncertainty, feed forward, and feedback, but also, and the key principles that feedback and feed forward enable. But I think that the architecture of how this connects together may be different. And the architecture that I usually use, those of you who've seen me talk about this before, in this particular case, actually doesn't look that unfamiliar. So here's a block diagram showing a bunch of systems, the blocks with some unmodeled dynamics, some nonlinearities, here modeled as static nonlinearities, connected with an interconnection matrix, that L matrix, and then a bunch of delays. And now what you should think about is, if this is a bacterial system, there are about 1 million elements, right, in the dynamics system, right? And so now you've got a 1,000,000 by 1,000,000 interconnection matrix that you get to design. What structure should you put on it? Right? If this is the brain, it's 10 to the 11th neurons. Right? So if you want to design something that looks like a neural computation, right, how do you decompose that problem? Right? At a very high level, maybe it looks like this, but what goes underneath, right, looks very different. So I think that that's kind of a different thing. Okay, so I told you a little bit about what we've done. I sort of want to wrap up. So I sort of started and told you a little bit about this experience, which for me was a very important one, of thinking about what the future might look like. I think we got some things right. I think we missed some things. I think by and large, the big picture there was pretty close, and it led to lots of advances. I've been very fortunate in my own career and in the things I've gotten to work on, to work across a number of different areas and to think about how some of the ideas that we articulated back in 2003 might play out, and whether that's in the sorts of architectures that have these layering and formal methods and other things that we might use for modern systems ranging from sort of flight control to self-driving robots to different types of Internet of Things architectures. That's one area, but also in these more novel areas, which in my case is synthetic biology, but for others of you is geoengineering, what are the actuators there, or quantum mechanics, right? You know, sort of what are the sensing mechanisms there and how does that differ, right? I think all of these are sort of interesting areas. So I'd like to end by just thanking a couple of people. So one is the various groups that have supported the research. So this includes AFOSR, and in particular, Mark Jacobs and Siva Banda have been extremely supportive in my interactions with the Air Force. The National Science Foundation, DARPA was an early funder of this work, the Office of Naval Research in the Army as well. We also received a lot of interaction and support from companies. So Get Industry to Support finally worked. It took about 20 years from when I first wrote it down, but they finally started helping out. And in particular, I'd like to acknowledge United Technologies, Northrop Grumman, IBM, and most recently Denso. And it turned out, and this is, I think, important for the field to think about, for me moving into synthetic biology, there were two enablers. One was the Army, interestingly enough, through the Institute for Collaborative Biotechnology that Frank Doyle actually ran for a while. And the other was the Moore Foundation, right? And the Moore Foundation gave some money to Caltech that allowed us to do that. And I think we have to think about as a field, how do we get money for doing blue sky stuff, right? That I can't tell you why this is beneficial to society right quite yet, but I think it probably is interesting, and how do we do more of that? And so I think that's something we have to think about. Of course, all of this is something that also was helped by a tremendous number of people. And so I'd like to thank just a few of them. And so one is certainly the group that I worked with on the future directions of control, and Carl Ostrom, Siva Banda, Stephen Boyd, Roger Brockett, John Burns, John Doyle, Mark Jacobs, and Gunter Stein. This really shaped my worldviews, and these were leaders in the field at the time that I was interacting with them, and they still are, of course. And really, I think that group and the broader group that participated in this made a huge difference. The other thing that I've been very fortunate to have in my career is lots of collaborations. And so I wrote down some of the ones where we've had joint students, joint papers, or joint projects, and I probably missed a few. But Caltech is a fantastic environment for doing that, and I've had many pleasant interactions with people across the spectrum in terms of their field and other areas. The Jet Propulsion Lab, which is nearby Caltech, academics that I've had joint students, postdocs papers, and other things with, and people in industry. And so a large group of people that have been really responsible for helping shape what we do, as well as the people back from my graduate school days, and Shankar Sastre, my advisor in particular, but also some of the graduate students that were in Shankar's group and nearby at the time. And finally, I'd like to thank the various students and postdocs. Here's a list of them. And so there are a couple. And so I've been, of course, fortunate to have many outstanding students and postdocs. You see, I hope all of them listed there. Everybody who's in the audience, check, and if you don't, come bang on me if I screwed up. And I've also had the pleasure of having a lot of undergraduates. So Caltech has a program called the Summer Undergraduate Research Fellowship Program, SURF. I've had about 150 SURF students over the years. This is a fantastic way to explore new areas, right? Because they do about a 10-week project, and then they go away, right? And so at 10 weeks, you know, you haven't wasted much of their life with some harebrained idea that didn't work out, right? And so I very much encourage everybody to do that. And I've had a huge number of visitors that have come over the years as well. And so with that, I'd like to thank you for your attention. I hope you got something out of it. Thank you very much.